Hello everybody, hope everybody is well. So this is going to be our first lesson for the higher course, and we're going to be looking at patterns in the periodic table. So you're going to need the following. You need a pen and paper, you're going to need your data book, and also a calculator. And we're going to be looking at three patterns in the periodic table. We're going to be looking at covalent radius, ionisation energy, and also electronegativity. So we're going to start with a few questions just to get your brain in gear. We've got 6 marks available here. All the questions are related to the topic that we're about to do. They're National 5 content, so you should be fine with them. Go through them at your own pace. So what I recommend is that when the question comes up, if you can pause it, pause the video and answer the question on a pen and paper, unpause the video, the answer will be displayed and you can mark it yourself. So here's the first one. So have a read, pause the video, and then have a go. Okay, so this question is all about something called the ionisation energy, which is one of the things we're going to look at today. And it says in the third sentence down, so the first ionisation energy for an element is defined as the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. And then we've got a question below it. An equation below it, and you'll notice that we go from a chlorine atom to a Cl plus ion, which is a bit unusual because normally we see the Cl minus ion, the chloride ion. And the question is to state the electron arrangement. Well, if the Cl atom has got an electron arrangement of 287 and the Cl plus ion has lost an electron, it's going to go to 286. So 286 is the answer for that one. And the next, write the equation for the first ionisation energy of magnesium. So we're going to start with the magnesium atom. It's going to be in the gaseous state. We're going to lose an electron, so just the 1 electron, and it's going to form the Mg plus ion. And it's important that you put the state symbols there too. So give yourself a mark if you got those two. Next question. So again, pause the video, have a read, and then unpause when you're ready for the answer. So we're continuing with the ionisation energy here, and the question is asking, describe the trend in the ionisation energy going down a group. So we've got 2 groups all mixed up here. We've got the alkali metals of lithium, sodium and potassium, group number 1, and then we've also got the halogens of fluorine, sodium and fluorine, chlorine and bromine. And you should notice for the trend for both groups is that as you go down, so you start from the top, so lithium for example, going down to sodium, the ionisation energy drops, and then going even further down to potassium, it drops again. So our answer is that as you go down the group, the first ionisation energy decreases. Okay, next question. So again, pause the video, have a read, and when you're ready, unpause. So energy is required to remove an electron from an atom. What happens to the energy going down a group? So we can use helium, neon and argon as labelled there. And as you go down the group, the energy decreases. And describe the general trend in energy going from sodium to argon. So this is going now across the period. And sodium is atomic number 11. So if we find atomic number 11 on the x-axis, and we go to argon, which is atomic number 18, we can see that the general trend is that it increases. So the quantity of energy required to remove an electron increases. So 2 points available here. Next question, and this is the final question. So pause the video, have a read, and when you're ready, unpause the video. So we can see here that as the atomic number increases, the melting point also increases. So fairly straightforward on there. So let's get started. So we're learning all about the periodic table. We're learning about some patterns that exist in the periodic table that you will not be familiar with. We haven't come across these at all before. It's always a good point to learn a little bit about the periodic table and also learn a little bit about the history of the man who invented the periodic table. It's a fascinating history. If this isn't for you, if you want to miss this without, then there are timestamps at the bottom and you can skip on, but it'll only take a minute or two. So Mendeleev was born in Siberia in a small little village, and he was one of 17 siblings, born in 1834. And he had a very difficult childhood. His father was blinded when Dmitry was a young child. He then died a few years later, leaving his mother to look after the entire family. But it was realized early on that Mendeleev was something of a child prodigy. He was very precocious. He was very intelligent, and this was quite obvious to his mother. So she realized that the place where they were, Siberia, was not the best place for him to reach his potential. So when they were young, they decided that Dmitry should go to Moscow. Now, from Siberia to Moscow is a huge distance, and this is the time before, this wasn't an industrial Russia, this is the time of horse and cart and bad roads, and it was difficult to get from place to place. But they traveled a huge distance over many, many weeks, and eventually they got to Moscow in the hope that Dmitry would be accepted into the university. But they turned him down. So they had to go to even further distance to St. Petersburg, where Dmitry was accepted into the university there. But tragically, his mother died not long after they arrived. Some say this is a result of the exhaustion of the journey of getting there. But he was accepted into St. Petersburg University, and he excelled in a number of fields: economics, physics he did a little bit work in, but mainly chemistry. And he was considered something of a polymath in that he was incredibly intelligent in lots and lots of different areas. And he worked on trying to order all of the known elements at the time, and he worked and worked and worked. And his story is that it came to him in a dream exactly in how to order the elements. Now, at the time, there were lots of other scientists who were working on their versions of the periodic table. But what set Mendeleev's version apart is the fact that he was able to predict the properties of elements that hadn't yet been discovered. And he predicted the properties of those elements there. So scandium, technetium, gallium, and germanium. And he predicted them with a very, very high degree of accuracy. And then later on, a few years afterwards, when they were discovered, people then realized, well, this is the periodic table that we've got to use, and we can discard all the other ones as well. So that's why we use Mendeleev's periodic table as opposed to anybody else's. So a little bit of backstory there. And the patterns that we're learning about here, Mendeleev couldn't have possibly known about them because there were discoveries that had yet to be made. For example, the electron had yet to be discovered. So it's even more impressive that we use his periodic table, and he was able to order all of these elements accurately because of these discoveries that had yet to be made. So let's move on. So the first part, we're going to break this lesson into 3 parts. The first part, we're going to cover covalent radius. And I want you guys to be able to do the following. I want you to be able to define covalent radius. I want you to explain the trends in covalent radius going across a period and also down a group. So let's go on with defining covalent radius. Now, the sort of questions that you can expect to see are as follows. So these are the questions I'd ask you to be able to answer later on. Let's see what it says. So question 1 is explain why the covalent radius decreases across a period. So why does that happen? And then also, why is the covalent radius of sodium larger than the ionic radius? So we're looking at, can you explain the trends in covalent radius going across periods? Now, our covalent radius is simply the measure of the size of an atom, how big it is. Now, we've seen previous models of atom looking like so. This is known as the Bohr model, and it's very, very similar, I suppose, in a way of thinking of how the planets move around the sun. And in this model, we have the nucleus in the center, and then we have these electrons going around in quite clearly defined paths. Now, when this model was proposed, this was believed to be as atoms are, but we've subsequently learned more about the atoms. We realized that's not actually what an atom actually is, what it looks like. We don't have these clearly defined boundaries in an atom. An atom is more like the following. Now, all of those little blue dots there, they represent areas where an electron could be, the probability. So the more dense the blue dots are, that means that the higher the probability of an electron being there. But it does mean that an electron could be moving around into different places. It could be at any one time, a lot further away from the nucleus than at another point in time. And because of that, we can't actually define where the edge of an atom is. And because we can't define where the edge of an atom is, we can't just look at single atoms and say this atom has a certain size, a certain width or radius rather. So we need to come up with a different method of how to measure the covalent radius. And the method that we use is by taking two atoms, and this would be in a molecule, I guess. This will be a molecule of hydrogen here, so H2. And you measure the distance between the two nuclei and then halve that distance. And that's a perfectly adequate way of measuring the covalent radius. So the distance between two nuclei of adjacent atoms is measured and then halved. Now, if you look in your data book, you may notice that there's no data for the noble gases. So why is that? Why do you think there's no data for noble gases? So pause the video, and then when you've got an answer, unpause, and we'll see what you got. So while noble gases, you may remember, are monatomic, which means that they don't bond with anything. So you cannot therefore have two atoms that were adjacent to each other. You can't get them next to each other. And because you can't get them next to each other, you can't measure the distance between two nuclei. So that's why we have no data for the size, the covalent radius of our noble gases. So here's a little question. We've got two atoms. We've got sodium, which has got an atomic number of 11, so 11 protons, 11 electrons, and 12 neutrons. And then we've got chlorine, which has got more. It's got 17 protons, 17 electrons, and then depending on which isotope, anywhere between 18 and 20 neutrons. So which do you predict is going to be bigger? Is it going to be sodium, or is it going to be chlorine, which has got more things within its atom? So pause the video. Now, I'm hoping that you decided that chlorine will be bigger because chlorine's got more stuff. But counterintuitively, if you look at the size of our atoms, we find that as you go across a period, the size decreases. So even though there is more stuff in a chlorine atom, it's smaller, which is a bit of a conundrum. So we're going to try and answer, why is it that chlorine, which has got more protons, more neutrons, and more electrons, why is that smaller than sodium, which has got less of these things? So here's our trend. As the size of the atom decreases as you go across a period. So why is that? So have a think what's going on in an atom. We've got positive protons that are attracting negative electrons, and that's what hold the atoms together. So again, just pause the video, and when you're ready, unpause, and you can have a look at the answer. So here are two atoms. We've got what do we have? We have sodium on the left-hand side, which has a nuclear charge of 11 plus, and then chlorine, which has got a larger nuclear charge of 17 plus. And it's the fact that we have more protons in the nucleus that means that it is able to drag those outer electrons and attract them strongly, more strongly than the sodium can. And so therefore, the outer electrons are pulled closer to the nucleus in chlorine than they are in sodium. Now, I should point out as well here, the only electrons I've included in these diagrams are the outer electrons, not the inner electrons. But they wouldn't make too much of a difference to the size in this case because we have the same number of electron shells in sodium and in chlorine, which is why they can be compared. But in summary for this one here, if we increase the nuclear charge, that attracts the outer electrons towards the nucleus. Therefore, in this case, the increased nuclear charge equals a smaller atom. Now, going down a group, we can compare, what do we have? We've got lithium and cesium in the alkali metals. And we can see this periodic table here. It gives us a way of, it represents the size of the atoms and how they're all different. But why do we think that lithium is significantly smaller than cesium? So pause the video and have a think. So here are two atoms. We've got lithium and we've got cesium. So lithium with its 2 electron shells and cesium with its 6 electron shells. And it's these extra electron shells that contribute to the larger covalent radius of atoms as you go down the group. And we can summarize this. We can say that across a period from left to right, the covalent radius decreases for the following reasons. So read this, please. And then as we go down the group, the covalent radius increases for the following reason. So that's covalent radius completed, and this is the question that we saw at the beginning. So if you can have a go at this question, so pause the video and then we will go through the answer in a second or two. So the question is asking you to explain why the covalent radius decreases going from sodium to chlorine. And then the second question is, why is the covalent radius of the sodium atom larger than the ionic radius of the sodium ion? So for the first question, why does it decrease as you go across a period? That's because we have a greater nuclear charge. The number of protons in the nucleus increases. And then for the second question, we have that the atom has lost an electron, and therefore we have a reduced number of electron shells, therefore it is smaller. So our next pattern that we're going to be looking at, our next trend in the periodic table, is the ionization energy. And we're going to do the following, so if you can read those success criteria, please. The type of question you're going to be asked is as following, as so. Now this here again is asking you to look at the trend in ionization energy going down the group, similar to the covalent radius question. So have a read of this, please. So ionization energy, let's have a look. So we've got this sodium atom here. Now, if this sodium atom undergoes, it's very reactive, and the reason why it's very reactive is because it's got this one outer electron, and it wants to have that outer electron removed so it can have a stable electron arrangement. And if its outer electron is removed, then it forms this positive sodium ion, and we have the electron that would be taken by another atom, chlorine, for example, to form sodium chloride. Now that electron doesn't just fall off, that electron has to be taken off, and that requires energy. Now the amount of energy required to remove the outer electron in the sodium atom is what's known as the ionization energy. And we can come up with a more specific definition for the ionization energy, which is as follows. So that definition is important, and let's highlight a couple of things. So first off, we're talking about removing 1 mole of electrons, and we're removing those electrons from 1 mole of gaseous atoms, and they will form a gaseous ion. And we can write that in an equation like so. And this equation tells us that 1 mole of gaseous sodium atoms are turning into 1 mole of gaseous sodium ions, and 1 mole of electrons are being removed. Now, the state symbols are really important. If you're asked to write the ionization energy for any chemical, you would be required to include the state symbols there. And we can also ionize, well, we can ionize any atom. And we've got the chlorine atom being ionized to the Cl plus ion. So just be aware that we can also form, so non-metals can also form positive ions. They can also be ionized, but that's more difficult, and that requires quite a bit more energy to do so. And we can actually see, as you look at the ionization energy across a period, we can see that the general trend is that as you go across a period from sodium all the way to argon, it gets increasingly more difficult, generally, aluminium, it dips down a little bit, but it generally gets increasingly more difficult to remove one of those outer electrons. What we're going to try and do now is we're going to try and explain why that is. Why is it harder to remove an outer electron from argon, for example, than it is to remove an outer electron from sodium? So here's our two atoms. We've got sodium with its 11 protons, and then we have got argon with its 18 protons in its nucleus. And it's these extra addition of protons that as you go across the period with each successive atom, you add one more proton, and that increase in nuclear charge means that the outer electrons are pulled closer to that nucleus. And we can write an equation for sodium, and there is the quantity of energy required to remove 1 mole of electrons, 496 kilojoules for every mole. And then our argon, with its increased number of protons, therefore increased nuclear charge, is much more. In this case, it's nearly it's over 3 times more the amount of energy required to remove that electron from argon, because the protons in the nucleus, their combined extra, in this case 7 protons, can pull those electrons and hold on to them significantly tighter. But what about going down a group? Well, this now is looking at the alkali metals. So we've got lithium, then sodium, then potassium, rubidium, and cesium. And as you go down the group, we can see here that the trend is that the ionization energy decreases. So in other words, it is easier to remove an outer electron from cesium than it is to remove an outer electron from lithium. But why is that? Why is it easier to remove that outer electron from cesium than it is to remove it from lithium? Here's our two atoms. Lithium with its 2 outer electron shells, or 2 electron shells rather, and to remove one of those electrons, or to remove the outer electron, requires 520 kilojoules for every mole. And then cesium with its 6 electron shells is less, it's 376. So why is that? Have a pause, or pause and have a think. Well, the outer electron in cesium is further away from that nucleus, and there's 2 reasons for why it's easier to remove the electron. The first one is there are more electron shells in cesium. That outer electron is therefore further away, and because it is further away, the nucleus cannot exert as big an attraction on that outer electron. Even though the nucleus is much, much larger in cesium than it is in lithium, that increase in distance away from the nucleus decreases its ability to hold on to the outer electron. But there is a second reason, and the second reason is because of the role that the inner electrons play in cesium. And these inner electrons are negative as well, and they are screening the outer electron from the nucleus. So that outer electron there has got all the inner electrons are blocking the attractive force of that nucleus on it. So we refer to that as the screening effect. And these 2 combined lead to the ionization energy decreasing as you go down the group. So here's our summary. As you go across the periodic table, the ionization energy increases. And as you go down the groups in the periodic table, the ionization energy decreases. Okay, so have a look at this here. We've got magnesium. Now we can ionize magnesium and remove 1 outer electron, the first ionization energy. But we can also remove more electrons. We can, well, in theory, we can remove all of the electrons, but we can remove 1 more electron, and then that will form the more familiar Mg2+ ion. So we've removed 2 electrons, and this is, or rather, the energy required to remove that second electron from the Mg+ ion, so to go from Mg+ to Mg2+, is known as the second ionization energy, and we can define that as so. And we can write an equation for that. Now notice again, we've got gaseous ions being starting with the gaseous ions and then ending up with gaseous ions. So here's our equation. So if you could use your data book and then go and have a look at your data book and have a look at the first ionization energy for any atom, and then compare how that is to the second and third and fourth ionization energy for the same atom, and see what it's like. And then also, can you have a go at explaining this trend? So pause the video and have a think. This should take a couple of minutes. So here's our graph for the second ionization energy. So let's focus in on magnesium. So we've got atomic number 12. Now, if you look at magnesium, the jump is from the first to the second ionization energy. There is a jump. For every single atom, it is more difficult to remove that second electron than it is to remove that first electron. Now, you may notice as well, we've got sodium, atomic number 11. There's a huge jump between the first and the second ionization energy, and we'll cover why that is in a little bit. But our general thing that I want you to get from this is that the second ionization energies are always larger than the first. Now, why is this? Well, here's our second ionization energy. We've got the Mg plus ion. We are removing an electron, and we've now got the Mg2 plus ion. And have a read, please. Now, if you remember back to that graph, we had a really, really big jump between the first and the second ionization energy for sodium. And let's have a think of what we've got here. So we've got our sodium atom, which has been ionized, and we're showing here on the left-hand side, we've got the Na plus ion with its 8 outer electrons. So we've got a stable, we've got a filled outer electron shell. Now, if we want to remove another electron, we have to break into that shell, stable and filled outer electron shell. And that's very, very difficult to do, and it requires a significantly more amount of energy than it does to remove that initial electron. So this is the reason why, or these are the reasons why, it's difficult to break into a stable filled electron shell, and also it is less well screened by the inner electrons. And this is why, if you are to remove an electron by breaking into a stable shell, whether that's removing an electron from the alkali metals, or from the group 2 elements, or group 3, and so on, it is very, very difficult to do. And there is always a huge jump between removing an electron from an unfilled to removing an electron from a filled outer electron shell. Now, one of the things you may be asked to do is to calculate the ionization energy, or the energy required to, in this case, to remove 3 moles of electrons from a magnesium atom. So what is the quantity of energy required to remove 3 moles of electrons from a magnesium atom? Well, the way that we do this is we break this down and think about what is actually going on here. Well, initially what we have to do is we take a magnesium atom and we have to remove that first electron. The amount of energy to do this is 733 kilojoules per mole. That's the first ionization energy. We then take that Mg plus atom and we remove a second mole of electron to form Mg2 plus. And then we remove a third mole of electrons from the Mg2 plus ion to form the Mg3 plus ion. The total amount of energy required to do this is simply the sum of those 3 ionization energies. So in total, to remove 3 moles of electrons from an Mg atom requires 9,922 kilojoules per mole. And this actually demonstrates what I was mentioning a couple of slides ago, in that if you want to break into a stable filled electron shell, it requires a lot more energy. And you can see that demonstrated by the jump between Mg2 plus to Mg3 plus. whereby in this one you would be breaking into one of the stable shells, and that requires a lot more energy. So let's have a go at some questions for this here. So which of the following equations represents the first ionization energy of fluorine? So you may wish to pause the video and then come back in a second. So our first ionization energy is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So we're looking for which of these here is gaseous atoms. Well, it's not A and B because they're both gaseous ions. D is half a mole of an F2 molecule, so not individual atoms. So the answer is therefore C, and let's just double check. So we've got 1 mole of electrons being removed. They're being removed from 1 mole of gaseous atoms, and we're forming 1 mole of gaseous ions. So C is the correct answer. Next question. So pause and then have a go. This should take you a couple of minutes. Okay, so write the ion-electron equation for the first ionization energy of sodium. And then the second question is, explain clearly why the first ionization energy of sodium is much lower than the second one. So we've got 3 marks available for that. So let's have a look at the answers. Make sure you included the state symbols for the top equation, otherwise it would be incorrect. And then take yourself through the marking instructions there. Okay, next question. So I believe this is the first one that was shown right back at the beginning of this. So explain why the first ionization energy decreases going down group 1. Again, pause the video and come back to the answer when you're ready. Okay, have a read of that there, please. Now this is a calculation here. So this time we're going from Al3 plus to Al plus. So our box here at the top, that tells us that if we want to go from, so the first ionization energy, so that's going from Al to Al plus, that requires 584 kilojoules per mole. The second ionization energy is from Al plus to Al2 plus, and then the third is from Al2 plus to Al3 plus. Now, if we're going from, let's say, from Al to Al plus, the first ionization energy, if you want to reverse that and go from Al plus to Al, then that will require the negative of that amount, so negative 584. So try and use that information to answer this question, please. So the way that we do this is we go from Al3 plus to Al2 plus. That requires negative 2,760 kilojoules. And then we add on another electron. We go from Al2 plus to Al plus, and that requires negative 1,830. So if we add those two figures together, that will give us an answer of D, negative 4,590 kilojoules per mole. So the third part of our passes in the periodic table, and the last part that we're going to look at, is to do with electronegativity. Have a read the success criteria, please. The sort of questions we could be asked are as follows. So let's take a look at electronegativity. So we've got here a molecule of hydrogen being represented, and we've got the 2 individual hydrogen atoms with their 1 proton in the nucleus, and we've got the shared pair of electrons represented by the dot and the cross. And what we find for a small number of molecules is that these shared pair of electrons are right in the middle between the two nuclei. They're equidistant from the nuclei. But that's only for a small number of molecules. For the vast majority of molecules, what we find is something like this. For example, hydrogen fluoride. Now in hydrogen fluoride here, on the right-hand side, we've got the atom of fluorine, and then the left-hand side, we've got the atom of hydrogen. And the shared pair of electrons are pulled right towards that fluorine atom. The nucleus is dragging them in, and the hydrogen is really struggling to hold on to them. It still is part of that bond. It's still got those electrons, but they're still sharing the electrons, but they're certainly more towards the fluorine. And our electronegativity can be defined as following. So let's have a look here. What's this asking us? So we've got to explain the differences in electronegativity between sodium and chlorine, so going across a period. Sodium has an electronegativity of 0.9 and chlorine is 3.0. There's no units for electronegativity. And then going down the group, we have fluorine, which is 4.0, so very high, the highest you can find. And then iodine is 2.6. So there's two questions here. One is, why does the electronegativity increase as you go across a period? In other words, why is chlorine more capable of dragging electrons in a bond towards it than sodium is? And why is going down the group, why does the electronegativity decrease? In other words, why does iodine struggle to hold on to its electrons relative to its shared electrons relative to fluorine? All right, let's have a think. So in sodium, we have got 11 protons, and in chlorine, we've got 17 protons in the nucleus. So for a very similar reason to the covalent radius, in that if you have more protons in the nucleus and you have the same number of electron shells, in other words, the screening effect is negated, then the greater the nuclear charge, the larger the nucleus in chlorine, can pull those shared electrons towards it more or better than the sodium could. Or simply, greater number of protons means a greater ability to attract shared electrons. Going down the group, what do we have here? Well, we've got fluorine with its 2 electron shells. It's got 9 protons in its nucleus. And then we've got iodine, which has got a much, much bigger atom. It's got 55 protons in its nucleus. And it's got 1, 2, 3, 4, 5 electron shells. So why do we think that fluorine has a greater electronegativity? In other words, why is fluorine better at pulling electrons, pulling shared electrons towards it than iodine is? Pause the video and have a think. And here's our reason. Have a read of this, please. So in summary, as you go across the period, electronegativity increases. And as you go down a group, the electronegativity decreases. So let's have a look at a couple of questions here. So atoms of nitrogen and element X form a bond in which the electrons are shared equally. So you're going to need your data book for this one. So pause the video and have a go. Well, if the atoms are shared equally, it must mean that the electronegativities are also equal. So the way that we answer this is we find the electronegativity of nitrogen, which is 3.0. And then we look to see is there which of these atoms here also has an electronegativity of 3.0. And in this case, it's chlorine. So if you have chlorine and nitrogen in a bond, so a molecule of NCl3, for example, then those electrons are going to be equidistant between the nitrogen and the chlorine. So this is the question we saw at the beginning. Which of the following atoms has the least attraction for bonding electrons? So using your data book, pause the video and then come back when you're ready. Okay, so what we're looking for here is the atom which has the lowest electronegativity value, because that would therefore have the least attraction for bonding electrons, and the answer in this case is silicon with 1.9. So here's what we've covered today. We've defined the covalent radius, we've explained the trends in covalent radius across a period and down a group, we've defined and written equations for the ionization energy, we've explained the trends in ionization energy, we've calculated the ionization energy, and lastly, we defined electronegativity, and we described and explained the trends in electronegativity across periods and down the groups. So thank you very much for listening, for watching, and if you've got any feedback, I'd love to hear it.